In this video lesson, we're going to learn about transition metals, and we're going to take a really long look at the first row, at least, of the D block elements. And we'll learn that not all D block elements are transition metals, but all transition metals are D block elements. So the transition metals are found in the D block of the periodic table. So that's that section that dips down from after the alkali metals, but before the group 13 elements. They're moderately reactive, so not very reactive. They're framed on either side by the really reactive metals of group 1 and 2, and then the halogens are further down, group 17. Because they're not as reactive, they're very useful in construction materials. So one example of a transition metal is steel, which is actually an alloy of iron. It drove our industrial revolution. And you can go look for a video. It's linked in Cognity called The Making of Steel, and it's quite informative about how steel, the formation of it, and the discovery has transformed the world. So this was something that actually was new to me. Not all D block elements are transition metals, even though the heading over that section in the periodic table always says transition metals. But all transition metals are D block elements. So a D block element can have a complete or an incomplete D level. Transition metals have incomplete D levels in one or more of their atoms or cations. So that's what makes something a transition metal. So when we look at the first row D block elements, you can see here, these is their 3D section and then the 4S. Note that most of the elements have incomplete D blocks, so they're all transition elements, all of these. Now, the exceptions are copper and zinc. So copper has a full D block because it does that exception. So it takes one of the electrons from the 4s orbital and fills up the last spot in the 3D. So it has a full one. And then zinc has a full one because it's the last element in the D block. So remember, to be considered a transition element, the element has to have either an incomplete D block in either its atom or one of its ions. So copper is actually a transition element, even though it has a full D block as an atom. And the copper 1+ cation also has a full D block, so it loses the 4s1 electron to become copper 1+. But the copper 2+ cation has an incomplete D block, so it's lost one from the D block as well. So copper 2+ is argon with 3D. But zinc is not a transition element because a zinc atom has a full D block. So it goes zinc, argon, 3d10, 4s2. And then the zinc 2+ cation also has a full D block. It loses the 2 electrons from the 4s, not the 3d. So because transition metals have unpaired electrons in their D block, they have some unique properties, which we're going to explore more fully over the next few minutes. So the first one we'll take a look at is that they have variable oxidation states, as we've explored in our oxidation reduction unit. We also know that we're going to learn that they form colored complexes. So that's due to something known as D-level splitting. They can also act as catalysts in either elemental or compound form. They form complex ions when they're in solution, and they have magnetic properties. So some of these we'll take a look at during this video, and some of them, the magnetic property ones for sure, we'll save for our lesson on magnetism. So the first thing we're taking a look at is the variable oxidation states. So transition elements have more than one oxidation state, or at least some of them do. And that's because there's little change in energy between the 4s and the 3d energy levels. So all the transition elements can lose 2 electrons from their 4s orbital to become stable cations. And the exception is scandium. So all of these oxidation states are found in the data booklet under section 14. You can see that some of these oxidation states, some of them have many, like manganese, for instance. Most have just 1 or 2, so iron 2 plus or 3 plus, cobalt 2 plus, 3 plus. So because they can lose electrons from their 4s orbital first and from the 3d, then you can have so many different oxidation states. So if you take a look at the atomic radius trend for the period 4 elements, you can see potassium and calcium, there's a big change, but across the transition metals or the 3D section, there's very little change, and that's because the electrons are being added to the 3D sublevel, and the effective nuclear charge of the outer 4s sublevel is relatively constant. So there is very little difference when you take electrons away from or being added to this section here. The same thing with the ionization energy trend. Because the D block elements have similar atomic radii, the ionization energy trends are also quite similar. So S block elements have only 1 oxidation state, but transition elements can have many. So when you compare magnesium with titanium, magnesium is the blue line, titanium is the reddish pink line. Magnesium has 1 oxidation state of 2 plus, and after the second one, when you go from 2 to 3, you see a big jump in ionization energy. But if you take a look at titanium, it has 3 oxidation states, 2 plus, 3 plus, and 4 plus, so you don't see that jump in energy until the 5th electron is removed. So with magnesium, the first 2 are relatively easy, but then it's harder after that because it only has that 1 oxidation state. Titanium can have an oxidation state of 2, 3, or 4, so you can take those that many electrons off and there won't be much of an energy change, but there is a jump in ionization energy when you have to take the 5th one away. So for some extra practice, you can complete sections 13.11 and 13.12 from Cognity.